have two populations. This is what's happening. We got two populations and they're normal. So we got normal number 1, and then we have normal number 2. Okay, so that means that this has some mean value there, we'll call it mu sub 1, and some sigma value, we'll call it sigma sub 1, and this has some mu value, we'll call that mu sub 2 and sigma sub 2. Okay, again, the notation is pretty heavy here, so you got to keep track of things. The little subscripts indicate these two populations. Okay, now we take samples from each population. So we take samples here of size n equals to, I don't know, how about 8? Call that n sub 1. And let's say we take samples over here of something, I don't know, let's call that n sub 2, and we call that, say, 10. Okay? And so for every sample of size 8 we take from this population, we're going to have some x bar and some x. Again, we're going to keep the little subscripts of 1s there to indicate that those come from this population. And then we do it again, and we get another x bar sub 1 and another s sub 1, and so on and so forth. Same thing over here. We get x bar sub 2 there, some s sub 2, another x bar there, sub 2, s sub 2, and we do that over and over again. And just like before, what we're going to do is we're going to take the results from one population and the results from the other population, and we're going to subtract them. We're going to see what happens when we take x bar sub 1 minus x bar sub 2. So that's what we're going to be looking at. Okay, so we get some number there, we get some number there, we subtract them, we get a little value there. We do that over and over and over and over again for all these subtractions, and then we graph them. And just like before, we would see that this is a nice normal distribution. Right? So it's a nice normal distribution. This is going to be a case where every one of these little values on here represents an x bar minus x bar sub 1 minus x bar sub 2. Right? Every one of those dots represents what happens when you subtract these two values. Maybe I should put some numbers in here just to feel like I might be losing some people here. I don't know if this will help, but let's just say this is centered at, I don't know, how about 9 with a sigma of 2, and let's say that this one is centered at 7 with a sigma of 3, I don't know. So let's say I take a random sample, and in my random sample for the first one under this population, and maybe I get an 8. And then over here, maybe I get a 6. And then over here, maybe I get, I don't know, a 9.3. And over here, I get a, some other random value. Let's get a 5.9 there. Okay, so now I subtract them. So in this case, x1 bar minus x bar 2. So in this case, I would get 8 minus 6, 8 minus 6, which gives me 2. And then in this case, I would subtract the 9.3 minus the 5.9, which gives me, is that 3.4? Right? Okay, so now these are the values I graphed. The 2, the 3.4, those things get graphed on here. And after we do this for a very long time, we'll get a nice normal distribution where the mean of this distribution, and again the notation gets really ugly, it's mu sub, and then we put this guy, x bar 1 minus x bar 2 in the little subscript of that. Okay? And then we have a sigma of that, sigma of x bar 1 minus x bar 2. Okay? And so this is going to be equal to mu sub 1 minus mu sub 2. That makes sense. Right? If all we're doing is taking random samples from this population, random samples from this population, and at each point we subtract them and get a little value, graph it, little value, graph it, then it makes sense that the center of this distribution would be equal to the subtraction of those two values. In our case, it would be 9 minus 7, so it would be centered at 2. Got it? And then the standard deviation of this distribution Well, that's going to be equal to the square root of that, like that. That's what I want. Okay. All right, but now what we're going to be working with is, well, what if we don't know these values there, right? For our purposes, we don't really know the value of this, the mean of that population, or the mean of that population right in there. So just like before, we're going to say, well, we don't know what they are, but we're going to assume that they're equal to each other. For our purposes, we only work in cases where our assumption is that they equal to each other, which means that when I subtract them, they'll be equal to 0. Which very conveniently will mean that this will be centered at 0, just like before. All right? And now what about this? Well, just like before, well, since we don't know the value of mu or sigma for either population, we're going to use the information from our sample. And so for us, we're going to approximate it to be equal to s sub 1 squared over s sub 2 squared. And that'll be our best approximation for the standard deviation of this distribution. However, now that we're making all those guesses, we're guessing information about mu, we're making assumptions about the standard deviations of both populations, we know that this is no longer going to be a normal distribution. It stops being normal and it becomes a t distribution. So this will be a t distribution. Degrees of freedom, we'll come back to that in a second. Degrees of freedom. And so now this is going to still be equal to this formula, but we're assuming that mu sub 1 equals to mu sub 2, so for us it'll be centered at 0. But it'll be mu sub x bar 1 minus x bar 2 is equal to mu sub 1 minus mu sub 2. In our case, that'll be 0. And sigma x bar 1 minus x bar 2 is going to be equal to s sub 1 squared all over n1 plus s sub 2 squared all over n2, and then we want the square root of all that. Good? All right, so it's a t distribution where it's centered there. We're going to have one sample value in this distribution, and then we want to find the likelihood of that result. Well, what do? We standardize it. So what's going to be the standardization of it? Well, let's say that we are given some value over here. We'll have some given value, x bar 1 is equal to 8.5. And some other given x bar value 2 is equal to, I don't know, 8.7. So that when I subtract them, I'll end up with I'll end up with 8.5 minus 8.7, which is equal to negative. Remember, we're allowed to have negatives because we're subtracting them. Minus 0.02. Oh no, not 0.02, just 0.2. And so that's a value in this distribution. Say it's over here, negative 0.2. And so I want to know the likelihood of getting this kind of a result under my sample. This is the given sample. What's the likelihood that I would get this kind of result under the assumption that these two populations actually have the same population mean, which means this will be 0 for us, and this will be the standard deviation of that distribution. All right, so the equation is going to be to find this distance and then divide it by the standard deviation so we can standardize it. And so our formula is going to be equal to T sub naught is going to be equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by this ugly thing, which is s sub 1 squared over n1 plus s sub 2 squared over n2, and we want the square root of that whole thing, right? But notice the t value, a standard t value. Good, so that'll be the formula we use. And again, for us, this is equal to 0, so it simplifies life just a little bit. Good, questions? And then finally, the degrees of freedom is going to be equal to the smallest of the two, I believe. The smaller of the 2 degrees. So if over here this is 8 and this is 9, this represents a degrees of freedom of 7, 1 less. And this is degrees of freedom of 9. We take the smallest of the 2. So in our case, in this particular example, we would work with degrees of freedom equal to 7. The smallest of the 2 sample sizes is the one we use for our degrees of freedom. Okay, so this is just the concept, not what you're supposed to write down, and hopefully an explanation of where this formula comes from. Any questions about the idea? It's very similar to before, right? And remember, this is all under the assumption that these two populations are independent of each other. Both cases we've done so far are under the assumption that we have two independent populations.